We want to talk about proof by mathematical induction. And this is an example. You should prove that 1 plus 3 plus 5 plus and so on plus 2n minus 1 is equal to n squared. Alright. Now, the process of mathematical induction is to prove that when n equal 1, your statement is true. No, it doesn't mean that it's true for n equal 2, you know. And even if you say you prove that n equal 2 is true, it does not mean that it is true for n equal 3. Alright? So these are just conjecture, because you're giving an opinion or coming to a conclusion from incomplete information. Alright? Even if you prove that it is true up to 100, it doesn't mean that it is true for 101. So mathematical induction is a solid argument proving that this statement is true for all numbers n. So here, basically, you prove that it is true for n equal 1. Right? So you prove that n, or let's say you prove it is true for n equal 1. Then, or let's say Pn, because we generally use P, is a P. You can think of P as meaning a proposition, you propose an idea. No. You assume the statement is true for Pk. In fact, Pn is when n equal 1 is P1. You prove that it is true for n equal 1. You could prove it is true for n equal 2 if you want, or n equal 3. Right? But it does not mean that it is true for the next number. So what you do, assume that it is true when n equal k. You use k, you don't want to give a specific number. Right? K can be any number. Maybe it is 2. You prove it is true for n equal 1. So if you make k 2, k can be any number. Could be 2, 3, 4, 5, whatever number. If you make k equal 2, it proves that it is also true for n equal 2, and so on. But no, it's not complete yet. You need to prove that the statement is true for the next number in line. The number after k, pk, would be pk plus 1. You prove it is true for pk plus 1. Pk plus 1 follows k. Alright? So, let me just draw a line around this. I don't want to erase it as yet. So here now, 1 plus 3 plus 5 plus and so on. What this example is saying is that these are odd numbers. The sum of the first odd number is 1 square. The sum of the first two odd numbers is 1 plus 2. the first two odd number, 1 plus 2, right? The first odd number is 1. 1 plus 3. Oh, 2 is not an odd number. 1 plus 3 is equal to 2 squared. 1 plus 3 is 4 and 2 squared is 4. Good. The sum of the first 3 odd numbers is, well, the first 3 odd numbers are 1, 3, and 5. So 1 plus 3 plus 5 is what? 5, 6, 7, 8, 9. Is 9. So, but the sum of the first 3 odd number is equal to 3 squared. So it seems to be working out so far. The first odd number is 1, 1 squared is 1. The first two odd number is 1 and 3. 3 and 1 is 4, and 2 squared is 4. The first 3 odd numbers are 1, 3, and 5. 1 plus 3 plus 5 is 9. And when you say 3 squared, you give 9. If you should try the fourth one, we're not really doing it directly, no, you know. We're just examining this example and see what it is saying. The sum of the first 4 odd number should be 4 squared, right? Let's see, what are the first 4 odd numbers? 1, 3, 5, 7. Do they really add up to 4 squared? 4 squared is 16, right? 7, well, 7 and 3 is 10. 10 and 5, 15 and 1, 16. Yes, it works so far. It's working. But it's still not proved, because we did the first 4 odd numbers. How you know it is true for the first 5 odd numbers and so on? Alright, so let's see what's going on here. Let's erase these things. By the way, this 2n minus 1 business, how did they come up with that? First odd number, 1. When n is 1, 2 times 1 minus 1 is 2 minus 1 is 1. Okay, no problem. At 3, 2 times n is 2. Remember, these are the n position. N is 1 here, n is 2 for 3. 2 times 2 minus 1. 2 2 4 minus 1 is 3. Okay, fair enough. That's 3. The fifth, the 5, I mean, is in the third position and is 3. So they get that from, for the 5, it is 2 times 3, the position n, 3 minus 1. 2, 3, 6 minus 1 is 5, right? Okay, so we see why they put it as 2n minus 1. Alright, so let's see something here. You prove that P1 is true. How you do that? You say 1 is the sum of the first one odd number, is the first odd number, is equal to 1 squared. Good. Alright. So 1 squared is 1. So 1 is equal to 1. You prove that it is true for 1. Now, assume that P of some number, some other number, you don't want to specify a number, say K. Assume that PK is true. Okay. Now, if you assume that PK is true, and you could very well substitute K for N in the problem you are given. 1 plus 3 plus 5 plus, and so on and so forth, plus 2k minus 1 is equal to k squared. Alright. But then, what is the number that comes after k? It is k plus 1. So, what you must do Let me just cover this. What you must do, prove that pk plus 1 is true. Alright? Now, the first numbers are 1 plus 3 plus 5 plus and so on plus 2k minus 1 plus, no, the pk plus 1. You're going to replace k with k plus 1. It's going to be 2. You have this bracket, 2k is going to be k plus 1. Close that bracket. Then you have this minus is going to come here. Minus 1 is equal to, this k is no longer k, it is k plus 1 squared. Alright? So notice this part here, the 1 plus 3 plus 5 and so on plus 2k minus 1 is like this part that you were given, 1 plus 3 plus 5 plus 2n minus 1 equal to 1 squared. Now, it is also like this part. You have the 1 plus 3 plus 5 plus that plus 2k minus 1. You have 1 plus 3 plus 5 plus that plus 2k minus 1. See that? Now, here, this part, you know, is equal to what? It is equal to k squared. This is it, you know. It's k squared, right? You're going to have to set up the math so that you have an equation and you prove that the left and right hand side are equal. Right? Alright, now, okay, you prove that. Basically, you prove that already. This, you're saying that you prove it, but you want to show it clearly. You're proving that 1 plus 3 plus 5 plus and so on and so forth plus 2k plus 1 plus open bracket 2, open bracket k plus 1, close bracket minus 1, close bracket is equal to k plus 1 squared. Alright? Now, it's not that clear. You need to clarify. Plus. Then you have the 2. Let me write this as a square bracket. 2k plus 1. Alright? K plus 1 in bracket. Plus, no, minus, minus 1 is equal to k plus 1 squared. Now, change only one side alone. Right? If you change up both sides, yes, you would show that it is true. But the more sophisticated way to do it is to leave one side as it is and change the other side to make it both sides look the same. And sometimes when you trouble interfere with both sides, you lose some values that you would have maintained otherwise, right? So let's change up the left hand side to look like the right hand side. Now, k squared plus, multiply out the bracket, 2 times k is 2k plus 2 times 1 is 2 minus 1. Alright, so what do we have here? Oh, k squared plus 2k plus 2 minus 1 is 1 plus 1 equal that. Right? It is equal to k plus 1 squared. Let's keep writing it. K plus 1 squared. Now, let's see what happens after this. This is quadratic, a quadratic expression in k. So, let's see if we can factorize it. Think of two numbers that multiply to give you 1. They multiply to give 1 and add to give 2. 1. Oh, it's 1 and 1. Alright. So we can say k squared plus 1k plus 1k plus 1 equal k plus 1 squared. So make sure you're following now. You see, I jump up here. So you see what we're doing so far. Now let's factorize these two. You have k outside the bracket and inside the bracket k plus 1. Factorize these. Or do you have outside the bracket? 1. We have inside the bracket k plus 1. Called k plus 1 squared. Now let's take the k plus 1 outside the bracket. It's a common factor. It's k plus 1. Once you remember your factorization of quadratic equations, you will have a problem with this part. And then inside the bracket k plus 1 is equal to k plus 1 squared. Good. So we can write, this is k plus 1 squared, k plus 1 by k plus 1. So it's k plus 1 squared equals k plus 1 squared. So it is proved. Alright? So let's just quickly review what's going on. You get this. To prove this statement by mathematical induction. Now, we must prove that it is true when n is 1. So that is P1. Prove that P1 is true. So you put in 1. Well, 1 is just 1. And it is equal to 1 squared. Okay, P1 is true. Now, you assume that some number k, for some number k, the statement is true. So you say pk is true. So now, you replace n with k. So you say 1 plus 3 plus 5 plus that plus 2k minus 1 is equal to k squared, right? And after that, you're going to prove that the statement is true for the the term immediately after k. So it's pk plus 1. You prove that pk plus 1 is true. You say 1 plus 3 plus 5 plus that plus 2k minus 1 plus, and then you put in the term that comes after 2k minus 1. So that term is where you replace k with k plus 1, because you're counting up and you reach k, the next term would be k plus 1. So it's 2 times k plus 1, then you have the minus and the 1, you close the bracket, equals, well, since this is where you're stopping, it's a k plus 1 squared. When you stop at 2k minus 1, you get k squared. When you stop at 2k plus 1, it is k plus 1 squared. Right? And then you recognize that this part is really this part. So you can write k squared instead of the series here. So it is k squared plus, and then you have the 2k plus 1 minus 1 equals k plus 1 squared. Right? And then you want to manipulate this thing so that you clearly show that the left and right hand side are the same. They are the same, no, you know what? It's not that obvious. So you say k squared, you multiply out the brackets, and you get k squared plus 2k plus 2 minus 1, which is k squared plus 2k plus 1. And that on the left equal k plus 1 squared on the right. Now, you want to come right down to showing it. Right, exactly. So you factorize the k squared plus 2k plus 1. You get k plus 1, then you write it as k plus 1 squared equals k plus 1 squared. And that is your proof. I will see you in the next video.